Hi guys, today we're going to do a little review of what we did in class this week. This covers first day of class, which was the 13th, through yesterday, which was the 15th, Monday, Wednesday. Essentially the first day of class we just did a little bit of Gen Chem review and syllabus stuff, so there wasn't a lot of content. The second day we finished up with our Gen Chem review and then actually did all of Chapter 1. So I just want to hit the high points of what I think is important from our Gen Chem review, just to refresh your memory, in case you forgot, in case there's some holes in your notes or whatever, and then we'll take it from there. So the first thing that we covered that I think is important, or very important, is the table of electronegativity. Right. We're going to use electronegativity a lot throughout the semester, and so a quick list, very useful to have in your brain. Again, I'm not a fan of memorizing things, but I think this is really important to note. So I'm going to write them down here so we can reference them. Later on, when we're doing lots of different types of chemistry, we're going to have to kind of reference this general list as to why the chemistry happens the way that it happens. So the most electronegative over here at fluorine, least electronegative all the way at the other end at hydrogen. We talked about equilibrium a little bit, but I'm going to skip over that. I want to skip down to orbital shapes. Again, this is just supposed to be review. So we talked a lot about where the shapes come from and what they are, but the key shapes to remember are that s orbitals are spherical and a nucleus in the middle, and p orbitals, of which there are three of them, specifically px, py, and pz, are all the same as each other, i.e. they're degenerate. They just have different orientations in space. Right? One goes up and down relative to the plane that I'm drawing. One goes left and right relative to the plane that I'm drawing, and one comes out and goes in. That would be the PZ orbital as I've drawn it. So those are the take-home messages about our orbitals and orbital shapes. P orbitals are going to make all the difference in OrChem 1. That takes care of that. The next thing I would like to cover are the intermolecular forces. This is a little bit more important for lab, but also does have some implications in class, so I just want to write them up again one more time. Strongest intermolecular force is an ionic force. That's because you have a full formal negative charge, a full formal positive charge interacting with each other. That's a very strong interaction. The next one is hydrogen bonding. One hydrogen bond is not really that strong, but many hydrogen bonds together collectively have some strength. That's actually what holds DNA together as well. So hydrogen bonding is this interaction here between the partial negative of the oxygen and the partial positive of the hydrogen. The next intermolecular force is, I think, a combination of two forces. It's ion dipole. Right? I think in lecture I might have just summed it up to four forces. 4 or 5, doesn't really matter. Ion dipole is a combination of the dipole-dipole force and the ionic force. So the ion dipole would be something like sodium plus with like water, for example, which has a strong dipole. Dipole-dipole then would be something like, I think in class I used an ether as an example. Oxygen is electronegative. It pulls electron density away from this R group. R group is just a bunch of carbons, and so partial negative on this oxygen, partial positive on this R group. That's a slight interaction. That's the dipole-dipole interaction. And the last one is London dispersion forces, or van der Waals interactions. It's the thing that all molecules have, because all molecules have electrons by definition. So I think I used hexane or something like that in an example in class. Hexane has kind of like an electron density bubble surrounding it. Those bubbles don't necessarily want to be around each other, but if they have to be around each other, they'll find a way to make it work, and so that's the London dispersion force. It's not a particularly attractive force, it's just what happens. Okay? So those are intermolecular forces, not intra. Remember the difference. The next thing that we talked about that's also very important is Lewis structures. Lewis structures. So like I was saying, Lewis structures. Sorry, I had to pause the video and let my dog out. Lewis structures. Right. So in Gen Chem we have the rules about drawing Lewis structures, like the least electronegative atom goes in the middle for organic chemistry. Usually that's carbon, so if we were to draw a phosphate, for example, in Gen Chem we put the least electronegative phosphorus in the middle, surrounded by all single bonds, then we fill in our lone pairs. Double bond as necessary, fill in the octets, and then calculate formal charges. You can do all that stuff on your own. If you do it for phosphate, PO4, 3 minus, you get something like that. In the OChem world, drawing Lewis structures is a little bit different. Right? So I gave you the example in class, methane. least electronegative. Usually least electronegative in the middle, with the exception here because the only other atoms are hydrogen, and hydrogen can only have one bond, so if you put it in the middle, that's all you have is hydrogen. So methane, you would draw it this way, add up your electrons, single bonds first, and that's what you get. Water, same argument, because it's hydrogen, oxygen goes in the middle this time. Add up the rest of your electrons, fill in the lone pairs, calculate formal charge, and you get something like that. So we're going to spend a lot of time drawing Lewis structures and then drawing them differently as well. Then I gave this example, acetate, CH3, COO minus. Right, the acetate ion looks like this. And if you remember, I said there are a couple different ways that you can draw this ion. Right, you can draw it this way, or you could draw it this way. How are they different from each other? And everyone agreed and remembered, which is good. Oops, that should be a single bond. Let me clean that up. That they are resonance contributors or resonance structures of each other. So single bond, 2, 2, 2. Gives you this. Good. All right. So we use the special arrow, the resonance arrow, to represent these two. And convention also dictates you put these little brackets around it, right? Later on, we're going to be drawing structures that have lots and lots of structures, right? A resonance contributor, or a structure that has, 4, 5, 10 resonance contributors. So the way that we say all of these are the same as each other is by putting them in these brackets. And then again, remember, we use our resonance arrow. It's a special type of arrow. It's the only time we use that arrow in chemistry. Okay? We call this thing collectively a resonance set. Right? So sometimes on a quiz or exam or something, I'll say, draw the resonance set for blah, blah, blah. That means you have to draw every single contributor. Or sometimes I might just say, draw 2 resonance contributors of blah, blah, blah. And then you just have to pick 2 out of however many there are. Okay. How do we convert from one structure to the other? That's where we involve the curly arrows, or the curved arrows. So curved arrow nomenclature is also going to be very important. Right. Remember, it must start at an electron source. So it starts at the lone pair and goes to the bond. It must go to specific location, right? It can't just float out into space. It has to go to a very specific location. These 2 electrons exist in this orbital are going into this new orbital here. That would violate carbon's octet, and so the electrons in the pi bond of the carbon-oxygen double bond go to the oxygen. That's how we go from this structure to this structure. And if I want to know how to go from this structure back to the other structure, I just do the reverse process. Something like that. Okay, good. That's all I'm going to say about curved arrows. I've gave a whole bunch of examples of good arrows and bad arrows, so I'll just do a quick one here. Example of good arrows. And we'll do water getting protonated by HBr. This is a good arrow. It makes a very specific claim. This is a good arrow. Makes a very specific claim. That makes me happy. Bad arrows. Bad arrows are things that you're like, I'm not really sure what's going on here. So my example for bad arrow was, I'll use the same molecules again. This one doing that, and then HBr doing something like that. Right? That's not even curvy. That's bad news. Please don't do that. That makes me frown. Okay. So if you remember last, I gave you, go to a new page, I gave you a list of stuff to memorize, your functional groups, right? The name and the structure. So the alkane structure, all carbon hydrogen single bonds, alkane. Then you have alkene, E-N-E, and alkyne, Y-N-E, for carbon-carbon double bond, carbon-carbon triple bond. Again, this is just a summary version. The ether is the COC, and the alcohol is the COH. Okay, so all the stuff you have to memorize. Then you have the doubly bonded systems. So you have the ketone, where the carbon that's part of the double bond oxygen has carbons on both sides of it, K-E-T-O-N-E. Or if one of these carbons is turned into a hydrogen, it becomes an aldehyde. It smells good. Aldehydes smell good in general. If you have 2 oxygens, then you can have things like carboxylic acids. Or if you replace the hydrogen with a carbon, then what you have is an ester. Esters also smell good. Esters and aldehydes make up most perfumes and other aromatic compounds and things like that. If we start introducing nitrogen, we can have carbon-oxygen double bond with a nitrogen. That's an amide, and there are different types of amides. Or if you just have carbon singly bonded to a nitrogen with single bonds, you can have an amine. And if you do the carbon-nitrogen triple bond, you can get the cyano group, also called a nitrile. Two names for it. We had a list of prefixes for carbons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And our prefixes were meth for methyl, eth for ethyl, prop for propyl, but for butyl, 5 is pent for pentyl, 6 is hexyl, 7 is hept, oct, none, and dec. Right? So this is a list of stuff you got to memorize. Put a little star by it for memorization. It may, wink wink, show up on the first quiz, just so you know. Alright, that was the end of the Gen Chem review stuff, so we started again to Chapter 1. Chapter 1, we talked more about resonance contributors, so we did something like, took ethene, that's the name of this molecule, eth for 2 carbons, ene because it's an alkene, and we said, what's the resonance contributor for ethene? Well, it looks like this. If these 2 electrons go to this carbon, I don't see why they would, because this carbon is the same as that carbon from the electron's point of view. But if they did that, you would get a structure that looks like this. This carbon losing 2 electrons, calculated its form of charge, ends up with a positive charge. This one still has a full octet, but only has 3 bonds, so he ends up with a negative charge. And you get a resonance set that looks like this. One thing to note about drawing resonance contributors, the sum of the charges on any given contributor has to be equal to the sum of the charges on all other contributors. So this one has a total charge of 0, this one has a total charge of 0, and so they're fine. If you make a mistake and you forget to draw a charge, when you say, oh, this one's -1, but this one's 0, I must have made a mistake somewhere. So it's a good little check that you can use to see total charge of 0 equals total charge of 0, or total charge of 1 equals total charge of 1, whatever. Right, and then we started to get into line angle structures. So I said, well, it's a pain in the ass to draw stuff like this. Taking time to draw hydrogens. Takes forever to draw every little hydrogen. So the resonance contributor of this guy, these electrons go over here, and that hydrogen, carbon, hydrogen, positive charge, single bond, carbon, hydrogen, carbon, carbon, double bond, hydrogen, hydrogen. Oh, my hand hurts from drawing so many hydrogens, right? So that is the same as, if and only if, this resonance set right here. Right? And we called this the line angle formula. Right? It's very handy. That's the way I'm going to draw a lot of organic compounds. And if you remember, when it starts to get larger compounds, right, if you want to draw a 6-membered structure, something like that, it's a lot quicker to draw the line angle formula like that than it is to draw all of those hydrogens in at every location. And that's only for 6 carbons. What about when we get to 10 or 20 or 40, right? Things get pretty absurd. All right, then we talked about acid strength, right? It's shifting gears a little bit. I know it's a little disjointed right now, but it'll start to link up more logically in the future, right? Acid strength, and I made you repeat this mantra. Hopefully you remember it. The lower the pKa, the stronger the acid. I don't have Parkinson's, by the way. That's the computer not registering the pen that I'm using. The stronger the acid, okay? Right. Just mutter this to yourself once a day, and you'll be fine. Okay, follow me on Twitter, and I'll tweet it at you. Okay, so we had things like HCl, really, really strong acid, pK of -7. Then we had things like, in the organic world, we deal with relatively weak acids. The strongest acid we get are things like formic acid or methanoic acid, which is what this one is called, has a pK of about 3.7. In the organic world, we often get to deal with really strong bases, which means they're very weak acids, such as CH4. If I try to rip a proton off that and give it CH3 and H+, it's not very easy to do. My pK is very, very high. Okay. We had a couple new terms. Nucleophile, we're going to use that one so many times. That's going to be one of the major words in this entire class. An electrophile, it's not as major as nucleophile, but in Chem2 we're going to use electrophile just as much, if not more, than nucleophiles this semester. So electro. And to put it simply, a nucleophile is just simply a Lewis base, right? So it's basically something that has a lone pair of electrons, and it can take those electrons and can stuff it somewhere and make chemistry happen. So we have some target, some carbon with maybe a leaving group on it. The nucleophile has to attack the nucleus, hence the name nucleophile, lover of nucleuses, right? It cannot attack hydrogens. That would make it a base, just a regular old Lewis base. And we use our correct earlier nomenclature to say, okay, carbon can't have a violated octet, and so the leaving group has to leave. Electrophile, on the other side of the coin then, is Lewis acid. The generic electrophile term, here's our nucleophile, is E+, right? And I give it a positive charge, electrons, phile, lover. So lover of electrons. It has a positive charge. That means it likes electrons. So it gives you something like this. And it creates a new bond. And that's one of the reasons that these things are so important in organic chemistry, is because it's a way to make new bonds. In Gen Chem, most of the bonds that you made were just acid-base chemistry, right? That's boring. We're going to make molecules now, big, large, complex things that solve the world's problems, right? Cures for cancer, etc. You can't do that unless you can control what bonds are being made and what bonds are being broken. Okay, so that was the end of Chapter 1. It was kind of short. Next time we'll get into Chapter 2 and then Chapter 3, something like that. We'll cover molecular orbital theory, hybridization, isomerization, polarity, intermolecular forces, a little bit more functional groups and all that fun jazz. So if you guys have any questions, feel free to send me an email. Remember, please use this email address. jursic.scc@gmail.com, and I'll get back to you as soon as I can. Good luck doing the homework. Just do Chapter 1 homework, guys, and that will be due on Wednesday because we haven't started Chapter 2 yet. Obviously, it can't be due, so I'll post on Canvas about that as well, but for now, I just want to let you guys know, just do Chapter 1. Good luck!